So hello everybody. Glad to see so many people, also people that I know when I go through the waiting room list at the moment. Yeah. Today we have Michael Kiessling from Rutgers, and as usual, Paula will take on the moderation and introduce our speaker, and then we follow along, Paula.
Okay, thanks, Dirk. So welcome everybody also from my side. So I'm very happy to announce today's speaker, Michael Kiessling from Rutgers University. So he's there as a mathematical physicist working in the math department. I'm very happy that you're here today. Let me just say a few words about the structure of today's talk. So there will be first a presentation on the perspective, so basically how this all fits into the larger picture of physics. And then we have a 5 minutes Q&A break, and then this is followed by a core talk, which is more technical. Exactly. And then there will be a Q&A afterwards, of course. So today's topic is the classical relativistic radiation reaction problem, and I'm very curious about the new recent developments in this field. So please, Michael, go ahead.
Thank you, Paula, for the introduction, and Dirk, and all the organizers for the invitation. And I'm very happy to be given that opportunity. And so, yeah, as Paula was saying, I will structure the talk into two parts, part one and part two. And for some reason, doing some last-minute edits here, you see the cell force. That shouldn't show up on that slide here. There's a copy-paste error, but I didn't have time to correct it anymore. So anyway, part one is for a more general audience, and part two, then it gets more technical, but I expect to spend about 20 minutes maybe on part one, roughly. We will see. So first, what is the big picture? So let's go back 125 or so years to the International Congress of Mathematicians in 1900. And so by that time, the atomistic explanation of matter had been pretty widespread accepted by physicists, not entirely. So 5 years later, with Einstein's PhD thesis on Brownian motion, that was really the turning of the tides. But in any case, to Hilbert, it was clear enough that the success of the Maxwell and Boltzmann approaches using statistical mechanics needed to be made rigorous. What he was postulating then in his so-called sixth problem is not postulating but proposing to lay the rigorous mathematical foundations of the macroscopic continuum laws of physics in terms of the Newtonian dynamics of a huge number of atoms. And as a side remark, it's clear that this is not really a problem in the same sense as Hilbert's problem number 8a, which is study the Riemann hypothesis. That's a very clear-cut problem. So the sixth problem is really an open-ended project, right? And in any case, so in this past 125 years, quite an enormous progress has been made. In particular, recently there was a lot of hoopla about the derivation of the Maxwell-Boltzmann kinetic equation and also the proof of its global well-posedness as an integral differential equation, the work of Hani et al. And also Silvestre and Villani on the well-posedness should be mentioned here. And so let's take this as basically the signpost that we want to keep in mind. And I will now update that to give you a modernized version of this problem to pave the ground for what we are after. So the modernized version is the Newtonian version still, is the following. So instead of hard balls that bang around in space, deflected from each other, so let's consider a huge number of point particles. Also, hard spheres can be considered like point particles with a very singular interaction that they interact when they have the distance that corresponds to their diameter and otherwise no interaction. So we take point particles and of 91 different types. They are charged, and the charges go from -1 to 92, with the exception of 43 and 61. These are the electrons, and stable nuclei, 43 and 61, are so radioactive that they don't occur in nature. So that's why 91 different types. And so the idea is that particles move through three-dimensional Euclidean space as time goes on. And of course, according to Newton's laws of motion, and you need pairwise forces between the particles. And we just take the electrical Coulomb forces. They can be repulsive or attractive and decay like 1 over distance square. We take Newton's gravitational forces, also like 1 over distance square, but they are only attractive. And since we don't use quantum mechanics here, we need to stabilize at short distance. So we introduce some stabilizing repulsive force that dominates the 1 over r squared term. Let's say we take just 1 over r cubed, but it has to be short range, so you also smack on an exponentially decaying factor. And so the units for r would be the size of typical atoms. So the question then would be, to which extent does this microscopic model account reasonably accurately, not perfectly, but sensibly, for the material phenomena in our world? So that's the question. So, and it's obviously clear that the Newtonian model will miss a lot of phenomena. But the question is not how bad that model is, the question is how good is it? So basically we will see it is very good, and it sets the reference standard to which one has to aspire to if you want to do better. So here's then the first observation. With the forces as I defined it, then you can prove, and I proved that in my course for graduate students in mathematical physics, that this model is, as a dynamical model globally in time, well posed as an initial value problem. So that means no matter where you put your particles, finitely many, and what velocities you give them, except you should not put any two particles on top of each other. So no two particles occupy the same position initially. Then you have a global evolution in time. So that means that is as good as it can get. And from now on, the question then simply becomes, if the initial data for these n particles are chosen to represent the state of matter today, do the dynamical equations correctly predict the state of matter tomorrow? And of course, today and tomorrow here, they are just metaphorically. So the question is, do the predictions come out right? And now, of course, one cannot expect that no matter how you start, you will always get the world coming out as we see it. You have to start that it corresponds roughly to what you see. And the important part is to keep in mind, when you look into the night sky, you see that matter is pretty clustered. It's mostly empty, the space. And then you once in a while see a star. And at a larger scale, it's similar. And so that helps so that you don't need to really take into account all the 10 to the 80 or whatever particles in that model all the time. So you can break it down in good approximation into sub-universes if you want, that have much fewer particles, and then they start to interact as a correction term and so on. So you can set that all up systematically. And the answer to this question Q prime, the A prime, is that this model actually does capture qualitatively and to some extent also quantitatively accurately the behavior of physical matter as we know it when you let n run between 2 and roughly 10 to 55. So 2, well, of course, that is the simplest you can think of. Electrons and nuclei bind to form atoms, like an electron and a proton, that you can show that they have a preferred state that is a bound state. And then you can go on and you show that neutral atoms in this theory bind to form molecules, which is what they should. You can also show that celestial size ground states exist, so that's where the 10 to 55 comes in, and that they are approximately spherical. And you can also show that two such ground states carry out approximately Kepler motions, which they should. And what is also expected that you can derive kinetic equations for plasma, let's say the classical electro-Coulomb plasma. You may expect to get the elastic equations of solids coming out. And so it's, of course, also an open project, but one can really show how much successfully comes out. And I myself must say that when I include here the small numbers, that I was very surprised. A few years ago, I got contacted by David Wales from Cambridge. He's a chemist, theoretical chemist. and with some questions, and we started a collaboration, and I learned that chemists, they do nanoclusters using Newtonian physics. So this is clumps of molecules, anywhere from 2 to several hundred or so. And the fact that a molecule itself exists, or an atom, so the so-called monomer, that's a quantum mechanical thing. And but once you have these monomers, how they bind, you put some effective models there, and they're all Newtonian, and they are quite successful at that. So I didn't expect how good Newton's physics is down to such small scales, but it apparently is. And good. So now, taking this as the role model, the next question is, around the same time when Hilbert had formulated his problem, and of course not my updated version of it, but also the electron had been discovered, and people tried to formulate a theory of moving electrons, the classical electron theory. And then in 1905 came special relativity, 10 years later, roughly general relativity. And so you would like to take the spirit of Hilbert's problem and now do the same problem, but in a general relativistic sense. No? So that's why I said quest for a relativistic version of Hilbert's sixth problem. And I mentioned here the Einstein-Infeld-Hoffmann legacy, namely, in some sense, they aimed in 1938 to lay the foundations for such a kind of problem. They claimed in a publication in Annals of Mathematics that the vacuum Einstein equation, so this is the Einstein tensor, I don't spell out the details from Einstein's field equations, so this G mu nu equals 0 away from singularities, that with these singularities representing uncharged point particles, so they claimed that they can extract the equations of motion of Newtonian physics from just these equations. And subsequently, Wallace, a student of Infeld, so he extended then the machinery that they were presenting to the Einstein-Maxwell field equation. Now the right-hand side is not zero, but it is given by the energy momentum stress tensor of matter, quote unquote. Matter in this case consists of the electromagnetic fields. In general relativity, you call even electromagnetic fields matter, so it's a little unlucky terminology. But they, of course, satisfy then the Maxwell Lorentz equations, meaning Maxwell's equations in vacuum away from the singularities. And so Wallace claimed that he can extract the equation of motion of charged particles from this. No? But when you take a careful look at these papers, I'm sorry to say, but this is voodoo mathematics, right? So this is just makes very little sense in some key steps. And and some of the results can just not be true. It's not only that they don't justify the results correctly, some of it must be plain wrong. So there is something that is a big obstacle, and that big obstacle is the radiation reaction problem. No? So just to take off from the ground, no? You need a well-posed, relativistically covariant joint initial value problem for the motion of massive charged point particles and the evolution of the electromagnetic and gravitational fields that they generate. And the classical radiation reaction problem is stood in the way. And here I put a picture in of Detlef Dürr. And Detlef was one of my teachers when I was a graduate student in Bochum, and we became good friends. And I was thrilled when in the mid-80s I heard him say what I put here as a quote, namely, when people realized that there is a problem, quantum physics was invented, then everyone started doing quantum physics, and the problem was forgotten, yet it still exists. And by that time, I myself, I had great problems understanding the textbook version of quantum physics. And so I decided I have to understand classical physics better. And then I ran into this classical radiation reaction problem and realized it had not been solved. And I decided I make this to be my problem. And then I run into Detlef and he says that this is a great problem. So I was hooked. And so I'm glad to report that with lots of persistence and stamina, so after more than 30 years of hard work, I can report some serious progress on this problem that was accomplished, in particular with collaboration with Shadi, Tahvildar-Zadeh. And we will report here in this talk later on that we have a well-posed initial value problem of a special relativistic classical electrodynamics of n-point charges in a BLTP vacuum. Okay, so now that doesn't stand for bacon, lettuce, and tomato sandwich with a pickle on the side, but it stands for Bob, Londe, Thomas, and Podolsky, who in the 1940s proposed to change Maxwell's law of the pure ether, as they called it, and to regularize the classical radiation reaction problem. And so they got some mileage out of it, but some serious problems had been left open, and those problems we solved. And then the question, once you have an initial value problem formulated, is, well, can you actually solve it, right, effectively? And so together with Holly Carley, Ryan McGigan, and recently Lilith Saxian, we have begun the evaluation of this electrodynamics in a very simple situation, but is a kind of a litmus test where you place a point charge in a constant applied electric field. Think of a condenser plate generated field, let it go, and what happens? And this can be solved. You can evaluate the forces systematically, but it's a huge amount of nitty-gritty work, even though at the end simple expressions come about so far. And then you put it on a computer and just solve it and plot the trajectories. No? So, but this is also only in the beginning yet. Then once you have the foundations on a microscopic level in form of this well-posed initial value problem for many point charges, now you can aim at the spirit of Hilbert's problem to try to extract macroscopic type laws. And since Hilbert explicitly pointed out as one example the kinetic theory of Maxwell-Boltzmann for classical billiard balls, so the analog would be the kinetic equations of a plasma, usually called Vlasov equations, and then comes whatever fields you take into account. So this would be the Maxwell, Bob Lundy, Thomas Podolsky fields, and together with Eve Elskens, so we have started to lay out a framework how to derive those, and we are pretty confident that that can be done rigorous. This part is not really totally rigorous, but we have little doubt that the absence and deltas can be supplied. And then the real question, of course, is general relativity. This here is special relativity all. Now, in general relativity, it's much more complicated. And together with Annegret, Burtscher, and Shadi, we have started, but these are baby steps. But even there, we made a little bit of a progress. But it's not BLTP, interestingly. And so we may be able to do something for BLTP electrodynamics there. So here's then also a few photos. Now here's Shadi with beard. That's as a co-author on the initial value problem of what I call BLTP electrodynamics. And then the evaluation of the BLTP motion so far, the publications are with Holly Carley and Ryan McGigan. I couldn't find a picture that shows them better. If I zoom in to make that large enough, then it's very pixeled and you cannot see much. So I left it with this nice landscape. My work on the kinetic theory is together with Yves Elskens from Marseille. And finally, the general relativistic is with Shadi and Annegret. And here I took a different picture so that you don't think you have seen that again. And yeah, maybe it's time, I would say, for taking a brief break. So I took only 15 minutes for this survey of the big picture before I get into any nitty-gritty stuff.
Okay, thank you, Michael. That was very nice, very interesting historical introduction. And now we are interested in your results. Shadi is also applauding. So there is one hand by Dirk. So Dirk, do you have a question or a remark?
Yeah, I would quickly like to ask a question about you said the well-posedness problem can be given a graded class or something like that. But do you really have in mind there the singular problems, also with Coulomb singularities? Because I would think that you have to have some entropic argument that so for almost all initial conditions you maybe have
Yeah, sure. It's not true. Sure, you have always so-called admissible initial data, no? So,
okay.
and the well-posedness is also only local in time, no? We cannot yet prove global in time in this case, just because one of the possibilities where things can go wrong is when two particles converge onto the same location. And so I will point these problems out in the technical part, no? That's
I
true.
see. And maybe a little follow-up question, if I may. The limits that you showed for n, they're from 2 to 10 to the 55 or something like that. Could
Yeah,
you
it's not a
comment?
limit. It's just a realm of
Yeah. Could you comment on what's happening then from for 10 to the 55
Oh,
on?
yeah. So this is 10 to 55 is roughly uh, when you start to see special relativity kicking in, even for the gravitational ground states. No? So
Mhm.
and you can imagine that you have application of this Newtonian problem with more than 10 to 55 also. But if you just look at gravitational bound states of many particles, then roughly at that realm, maybe 10 to 56 or so. So that doesn't come out so super precisely here. Then special relativistic effects soften the stabilization, the
Mhm.
mechanical stabilization, and you end up with a Chandrasekhar critical mass for so-called white dwarf stars, right?
Okay.
And so then and roughly at the same point, also then general relativity, of course, kicks in. No? So when you get to very uh, strong gravitational fields, no? And so that's why I put 10 to 55 as a rough cutoff there.
Okay. Paula, if there's no other question, and
Yeah, then
another
let's
very
go
quick
on. If there's no
question.
question, we just
No,
get to.
and allow me
Ah,
another
you
quick
want to have
question.
another question? Okay,
The,
let's
the
see.
the binding potential. Why is it chosen like 1 over r cubed? If I saw
Yeah,
this.
good question. I could, in principle, choose any power of r bigger than 2 to overpower the Coulomb attraction, right? And so the 1 over r to the cube is actually suggested by quantum mechanics. When you take the
Mhm.
Pauli principle for electrons,
Mhm.
uh, look at the Chandrasekhar theory of white dwarf stars, then basically that corresponds to a stabilization against the gravitational attraction by an effective 1 over r cube force at short distances. No? So
I
this
see.
is basically extracted from a continuum theory, you know? So it's the best you can do to match that. But for instance, chemists I mentioned, when they look at clusters, they don't take 1 over r cube. Typically, they take the Lennard-Jones interaction, which
Mhm.
has negative 1 over r to the power 6 attractive part and a positive 1 over r to the power 12 repulsive part. So they don't have anything like 1 over r cubed there. Uh, but the 12 and 6 has a very simple reason. The 1 over r to the 6 you can justify from quantum mechanics and to some extent from this Newtonian model that I had presented when the atoms are large enough, meaning Z is large enough, and so that you don't have a permanent dipole and not a permanent quadrupole. Then when you take two neutral atoms and put them far apart and ask do they have an induced dipole attraction then? And you can show yes, and that goes like 1 over r to the 6. But the 1 over r12 has only a simple reason that 12 is 2 times 6. So these chemists get a quadratic expression there, and you can use the quadratic formula for some computation. So it has really nothing to do
Mhm.
with deep physics, the 12. Okay.
Okay, thanks a lot.
Okay, so now I think, oh, any other question? No. So now we can then enter the core talk. So please.
Okay. Very good. So yeah, let's get into the little bit nitty-gritty part. So as for the details, okay. So the point is, of course, that this classical radiation reaction problem was encountered before even the advent of special relativity theory. So it came about in the near the end of the 19th century, there were already speculations because atomism got more and more accepted by the physics community as the explanation of what matter is made of. There were also speculation about what atoms themselves are made of, and that they should be electric was a suggestion that has been made. And somebody proposed that there should be atoms of charge, right? And so Stoney proposed to call those atoms of charge electrons. And that seems to be the only lasting contribution to physics that that man made. So the name stuck when the electron got discovered by Wiechert and Thomson and a few other folks, roughly at the time, 1897, I believe. And so now it was clear there is this very tiny particle, tiny object that is charged and has electric fields, and it moves and makes magnetic fields. And people set out to compute what they called the elementary fields or elementary laws of electrodynamics. It was Lienard and Wiechert independently in 1898. They computed the analog of what we would call the Green's function for the Maxwell equations at the time. Basically, when you work with potentials phi and a, so you have 4 times the wave equation. So it's almost Kirchhoff's formulas, if you want. And and then you find fields that are singular at the location of the particles, and they create a radiation field that is proportional to the acceleration of a particle. And so that was clear that these fields, they transport energy and momentum and angular momentum away. And so that had to be taken into account when you formulate an equation of motion. And that is exactly the problem that was encountered even before people discovered relativity, even though relativity was, of course, around the corner. And then came general relativity, and things get even more tricky there. But so one step at a time. So let's first review the so-called failed prototype, which is the Lorentz electrodynamics with point charges. There's also a Lorentz electrodynamics from the classical electron theory, which operates with smeared out charges, and that's a different story. I have some slide later on, and but I recommend the book by Herbert Spohn on the dynamics of charged particles and their radiation fields, where these type of approaches are considered. But I want to stick with point particles, and not because I'm obsessed with the idea that nature is truly consisting of points, but I definitely accept the idea that matter is made of tiny objects, right? Maybe singularities in space-time, and mathematically a point is the simplest way to express that something is here and not there. And so if for phenomena for which those tiny objects are far apart from each other compared to any possible size they have, working with points should be good enough to get a good theory, right? So that's what you should try first. Moreover, a point is a very simple thing, so that you don't need to worry about how it transforms under Lorentz transformation, for instance, right? So if you smear a particle out, different story. So let's take points. And so what would that be? So how would the theory be set up? And that's what people did from 1905 on. So I put 3 people that independently came to this conclusion, that there's a relationship between the velocity of a massive particle, so mass is non-zero, and its mechanical momentum, and it's given by this formula. And c is the speed of light. And you see, if you do let the speed of light go to infinity here, then this term vanishes, and you just get momentum divided by the mass, and that is the old Newtonian relationship. So you get Newton's relationship out in the limit as c goes to infinity. But what about p, the momentum? Well, Newton's law of motion, the law for the rate of change of momentum, is that the time derivative of p is given by a force. And now what is the force? Well, Lorentz wrote down this expression, and that takes fields, electric fields and magnetic induction fields, B, and that depend on time and space coordinates. you evaluate them at the location of the particle at time t. The B field gets multiplied in cross product with the velocity of the particle. Here's 1 over c as a scale factor, and the whole thing is multiplied by the charge of the particle. So that's the formula of Mr. Lorentz. And if the fields E and B are, let's say, Lipschitz continuous, meaning continuous with a bounded slope, then this set of equations for given fields E and B is actually well posed. So you have no problems with those. But, well, E and B are not given. They have to be computed. And so you compute them according to Mr. Lorentz, that you take the Maxwell equations with atomized charge density and current density. This is the current density here. So you have the fields E and B satisfying this partial differential equation with an inhomogeneity. These are the evolution equations. And then there are also constraint equations. Here's now the charge density atomistically written. And important is, even though we have them as functions of time and space here, but when you make sure that these constraint equations are fulfilled by the initial data, then you can show that a solution of these evolution equations automatically fulfills the constraint equation at all later times, by which I mean also you, in this case, assume that you would know how the particles move, how the motion q of t is given for each k, and therefore by derivative you get the velocities. So you have this term and that term, and so then it's just PDEs. You need initial data, of course, that are compatible, and the constraints for the initial data are here. Good. Now, there's a problem with the whole story, and that's the reason I speak of the failed prototype. So symbolically, these equations of Lorentz electrodynamics, they seem to pose a joint Cauchy problem, initial value problem, for the positions q of t and the momenta p of t, and for the fields B and E, initially constrained in the right way. However, the point is that these expressions are not defined. I call them infinite in all directions here. So I borrowed that from a book by Freeman Dyson with the same title. Charming book to recommend reading. And but what I mean by this is that in magnitude, if you let the space point S converge to Q, right, then in magnitude E and B typically go to infinity, and the direction of E and B, well, it depends on how you approach Q of t. So you can get almost any direction you want coming out, and so that's what I mean by infinite in all directions. So this is just not well defined. So, of course, when that was discovered, people had the option, get away with the point particle. And that's what I mentioned. That's what Lorentz did, Abraham, etc. And I'm not going in this direction, but smearing out a particle and then integrating over the charge density of the particle against the fields produces, of course, finite results then. But this is basically the same thing like averaging. And it's very popular, but you can show easily using convexity theory that the result that you get depends on how you average, and you can get anything you want basically if the fields diverge to infinity, and depending on how you approach the location of the particle, you can get any direction of the field coming out. Then you can get any force vector out that you want. So that means the right answer may be there, but if you don't have a compelling principle of how you have to average, then to just say, I need to average, is just an empty statement, right? So moreover, then there's some recent work by Dirk Deckert and Vera Hartenstein, who showed that even if I ignore the self-interactions, that means the point that I just mentioned, that these are ill-defined, and only talk about the fields that are produced by other particles acting on any given particle, you can show that given the information one has at the disposal for those typically initial data one picks, then that means position and momenta or velocity of the particles and their locations, and the fields initially are adjusted to it, then typically you will have field singularities that will propagate along the forward light cones of the initial positions. And that means as soon as one particle meets the forward light cone of another particle, it runs into such a singularity. And it has nothing to do with the self forces. So that is another reason why you get serious trouble with this Lorentz electrodynamics of point particles. And then, are there questions? I hear something. Maybe not.
No, I think that's fine.
Okay, so just noise. So another point that is also very important is that the fields actually diverge so strongly when the space point approaches a location of a particle, then that the energy momentum densities for the fields, these expressions, they are not locally integrable. And so therefore you cannot express a meaningful energy momentum conservation law. And so the upshot basically is that Lorentz electrodynamics with point charges is just not well definable. It has too many problems. And so what to do about it now? Okay, now clearly having Dirk as an organizer and in the audience, I cannot but have to mention a radical proposal that Dirk likes very much. Namely, it goes back to maybe even ideas of Gauss, as I read, and but Schwarzschild and then John Singh picked up on those. Fokker and Tetrode independently made a contribution, and I put a question mark here. So the radical proposal is to truly only take into account interactions from any particle on any other particle, but not particle on itself. Just ignore that. You also sacrifice the Cauchy problem. So I made a pun to say sacrifice Cauchy. Of course, he's long gone. You cannot sacrifice him. But so in 1903, Karl Schwarzschild proposed the law of motion. So he wrote down an action principle and using the retarded force of a moving point charge on another, computed with the Liénard-Wiechert so-called elementary fields formulas. And so the interesting thing, so basically that's a kinetic energy part that would be Newtonian here that he had in mind. But when you look at his paper, so he calls it, oh, this term is the die lebendige Kraft. That means something like negative 1/2 mv square. So that's a negative kinetic energy, which was called lebendige Kraft, means vivid force at the time. And so this term, of course, if you replace it by square root 1 minus v square over c square, then you have the relativistic version. So there's actually very little that needs to be changed to make Karl Schwarzschild's theory into a truly relativistic theory. And so it was in fact studied in the 40s by John Singh in a two-body situation. But a more radical version, even more radical than this, was then, it's a variation on the theme, was proposed by Tetrode and Fokker. They pointed out that this is Schwarzschild approach that takes only into account retarded contribution, and which of course was 1903, that is before relativity theory. So they in the 20s pointed out that by the space-time symmetries, one should stay symmetric with respect to retarded and advanced contributions. And so now they have a theory that is Lorentz covariant, but now it has both retarded and advanced forces. So the future talks back to the past. No? So clearly none of this is an initial value problem. That's what I said, you sacrifice Mr. Cauchy. And but what I think is more serious, as far as I can tell, there's no actio equals reactio. So there's no way to formulate a momentum conservation in this theory. So the experts presumably have looked into that, but so I didn't look to that too deeply, but I came to that conclusion, and I'm pretty confident that that conclusion is correct. So this is a serious problem, I see. So then came Wheeler-Feynman in the 40s, so they picked up on this Fokker and Tetrode theory. And so they formulated a selection rule, which they call the absorber principle. And this rule basically, in the net effect, is that it replaces all the contributions from the future by those of the past. And now a third-order time derivative term that looks like what you get from the Lorentz-Dirac equation of averaged Lorentz electrodynamics with point charges. So that's what I mentioned earlier. People love averaging over the neighborhood of charges a lot. And but now, well, still not an IVP results and still no action equal reactio term there. So, and there are lots of papers that come from the school of Detlef, Gernot Bauer, Bauer-Decker-Dürr, Bauer-Decker-Dürr and Günther Hinrichs. Nicola Wona is involved. So I've wrote a, and I'm pretty sure in the meantime there are more papers on those. And one comment is often you see Wheeler-Feynman in these titles, but most of the time it's actually for the Foucault-Titroud model. And anyway, so there's some work being done in that direction, and but all I wanted to do is mention it, and that's not what we are doing. So let's go back to the initial value problem font, and I put here Gustav Mie's legacy. That's in 1912, 1913, Gustav Mie proposed that all matter is actually electromagnetic fields. And so in order to get, well, not just linear superposition, he needed nonlinear electromagnetic fields. So he inaugurated nonlinear electromagnetic field theory. And so I already mentioned here, he purges point charges. He doesn't want anything externally put into the theory. And by modern lingo, you could say he was looking for field solitons. He, of course, didn't know he should call it that way. And that's, of course, a charming idea. And it was picked up in 1914 by Max Born, soon after David Hilbert in the 20s, Hermann Weyl also. And at some point, even Einstein wrote a paper about that. And so the main point is that when you work out a non-linear electromagnetic Lorentz covariant field theory, so you start with a Lorentz invariant Lagrangian. That's what Gustav Mie actually introduced, a whole family, a class of Lagrangian field theories. And it amounts to always getting the Maxwell equations in the general form in which Maxwell wrote them down, namely for electromagnetic fields in matter. And then there are some so-called constitutive laws, and they come out from the nonlinearity, from the Lagrangian. So I call them the vacuum laws, because we are not talking now about fields in matter. We will take point particles, and that means away from the points there is no matter. There is only the vacuum. And so I call them the vacuum laws. And so in 1933, I mentioned in 1914, Max Born picked up on Mie's work, and then he did other things, in particular in the 20s, working on quantum theory. But in 1933, Max Born says, the problems we have by quantizing electrodynamics are showing that the singularities that we encountered in Lorentz electrodynamics, they don't go away, so we are quantizing the wrong theory. We should go back to the ideas of Gustav Mie, and he puts the point charges now back in. And so Born's insight is that the non-Maxwellian vacuum laws can actually produce now integrable energy momentum densities for the fields of the point charges. And that was, of course, one of the problems that Lorentz electrodynamics had. So 1 year later, he gets joined by Leo Infeld, who modifies the theory a little bit, I mean the Lagrangian. Then, however, they have this nonlinear thing, and that's very difficult to handle. And in 1940, not long after, Fritz Bopp, in his habilitationsthesis, he points out, he says, this is a wonderful idea that Born and Infeld had, but the nonlinearity makes it so difficult to make any computational progress. I want a linear theory. Of course, linear is what Maxwell had, and he knows he cannot just take an algebraic law for the vacuum law. He says that has to come at the price of allowing derivatives. So he takes the linear higher order derivative model. 41, Alfred Landé independently apparently comes up with the same idea and gets joined by Llewellyn Thomas. And then Boris Podolsky jumps on the bandwagon and, in my opinion, makes some silly contribution. He makes some good contribution too. What is really silly is that he gives a physical interpretation of where that should come from, and he says it's neutrinos. So how on earth chargeless and almost massless neutrinos should modify the electromagnetic fields is a mystery to me, how that thought occurred to him. Okay, so let me explain what in words I had just said. Namely, all of these theories have one thing in common, namely, I mentioned the Maxwell fields of what Maxwell called field theory in matter, but now just in vacuum, but the vacuum, the so-called electromagnetic vacuum is different. So we have a Minkowski space-time, so it's all special relativistic at the moment. So we pick a Lorentz frame, what we call time and space vectors. And so then you assume that you have n time-like world lines that are the world lines of moving charged point particles. Time-like means that the speed of the particles is less than the speed of light. Now comes a point. Sorry for the pun, but point particles that move, right? So they have attributes like charge and mass, but they don't change, rest mass. And that means they don't get created or annihilated. They just move. So there's, in a weak sense or distributional sense, a continuity equation. So you can put together something that you can call the four current density vector, even though it's not a density, it's a measure, right? So you have charge density and the current density put together as a four vector. And it satisfies a continuity equation that is the four-dimensional divergence of a four-dimensional vector field being zero. And so there's an analog of what one learns in calculus, that if a divergence of a three-dimensional vector field is zero, then that vector field is locally the curl of yet another vector field. So there's a four-dimensional analog, and that goes under Poincaré's lemma. And even though the four-vector current density vector is a real, you can without problem assume that you can get it as the analog of a four-dimensional analog of a curl, not of a real, but of some complex vector field. So, and when you do that, that boils down to having four real three-dimensional vector fields. I call them DH and B and E.
Excuse me, Michael, I think there's a question. Maybe if you're willing to have a short question in between.
Sure.
Okay, Lorenzo?
Hi, Michael. Yeah, I'm curious about this Q dot that you put there. How I understand you want a classical theory, but how would you treat that in quantum mechanics?
Oh, let's not talk about quantum mechanics
now.
Okay,
cool. Thanks.
Good. So it's all classical here, no? So that quantum is on the horizon. No?
Right. Okay. Fair enough. Thanks. Good. Sorry. Thank you.
No problem. And so the point is that I said make complex fields. So the D and H are the real parts, and the B and E are the complex, the imaginary parts, basically. I pull them already apart. And so then when you do that, right, so you can express indeed, let's do it directly here. Here's the current density as a measure. Here's the charge density as a measure. So you express them as linear combination of time and space derivatives of these D and H right here. And here's D again. And the imaginary part gives you divergence of B being 0 and dTB equals that. And you recognize these are the Maxwell equations that Maxwell wrote down, except Maxwell, of course, didn't atomize the current density and charge density, but otherwise these are his fields. Even the notation of the fields is from Maxwell. But now you have the conclusion that just assuming there are particles that move through space, right, as time goes on, gives you these equations for free from mathematics. But there are two evolutionary fields, B and D, and then you have these fields E and H here. Where do they come from? That's where physics enters again. That's the vacuum law. So you need to postulate something. And here's what Maxwell did. He called that the law of the pure ether, and Lorentz said away from point charges, there's pure ether. So he took the same thing. So he just said H is B and E is D. Born and Infeld did something that you don't just dream up in the morning, right? So they came, as I said, from some Lagrangian, and they had some arguments that Ivo Bialnitsky-Birola once called one of the amusing stories of serendipity in theoretical physics. So the reasoning that they gave why they wrote down that particular Lagrangian did not uniquely lead to that Lagrangian, no? But there are 30 years later, or 40 years later, mathematicians and one theoretical physicist, Plebanski, independently they found 5 reasons that when you put them together, you get uniquely this. Born and Infeld didn't know that, but they hit the nail on the head somehow. So there's some compelling reasons to study this. B is a new parameter of nature. It's a field strength. And then the Bob-Landé-Thomas-Podolsky law is this. So this is the wave operator here. And so you see this is a Klein-Gordon operator actually acting on B gives you H. And in fact, this expresses H in terms of B. And then you have a Klein-Gordon operator acting on E gives you D. But this is actually an equation for E. So this looks symmetric, but is less symmetric than you would think to make it consist as an initial value problem. In this case, kappa is the Bob parameter, is a new parameter, and you get the Maxwell-Lorentz law when you let little b go to infinity in the Born-Infeld law, and you get also the Maxwell-Lorentz law from BLTP if you let kappa here go to infinity formally. Okay, good. So now the interesting thing is, even though they means Born-Infeld and Bob et al. Invented these non-trivial vacua to get rid of the non-integrable field energy density and field momentum densities, they did not pay attention to the Lorentz force. And all these write-ups, you see the Lorentz force popping up. But interestingly, different authors actually use the Lorentz force in different ways and also sometimes write different expressions for the force in terms of integral representations. Something that Landé-Thomas wrote down seems to, with hindsight, be justifiable, but only for scattering problems. But in any case, the main point here that I want to point out, when you have point charges, then the fields themselves still cannot be well defined at the location of the point charge. They may no longer in magnitude go to infinity, but they are still not defined. There is no limit as you let S go to the point charge. So the Lorentz force, cell force, remains not well definable. But already in 1902, Poincaré proposed a definition that was in a letter that he wrote to maybe Lorentz or so. And in 1906, it's published in his paper, this long paper on electrodynamics, where he basically has all the same formulas like Einstein, except that he still thinks about the ether. He doesn't really have relativity theory. So what Poincaré argues is he needs actio equals reactio. Remember, I pointed that out earlier. So he thinks of the following. There are 2 teams that are playing. There's a team particle and there's a team field. And whatever currency you use, right, momentum or energy, what team A loses, team B gains, and the other way around. So it's a null sum. So basically what he says is that since Newton said that the time derivative of the particle momentum is the force, right? So, and you want to have conservation of momentum, that means the negative of the time derivative of the field momentum should be the force, right? So that's what Poincaré said when you have a single charge. Now, this pi here is the field momentum density. And I wrote a nota bene here. So Poincaré died, of course, long before the Born-Infeld and Bob proposals appeared. So he worked with Maxwell vacuum. And not with point charges, but he worked with smeared out charges, similar to Abraham or Lorentz. And so later then he postulated so-called Poincaré stresses to keep those particles structurally stable. And the interesting thing, however, is if you change the vacuum law, then this definition can be used for point charges, and that's what we did. And it can be generalized actually to n charges. No? So that is not so clear, because momentum conservation is a statement about a 3-dimensional vector. So if you have n point charges, how can a single statement about a 3 vector give you n equation of motions? But I can explain that later. So here now are the expressions for those field momentum densities. Interestingly, for both Maxwell-Lorentz and Maxwell-Born-Infeld field equations, you get d cross b divided by 4 pi. I think there's a C missing here, so never mind. For the Maxwell-Bob-Landé-Thomas-Podolsky field equations, oof, a monster. Again, D cross B, but then you have E cross H and E cross B, and you have also the derivatives kicking in here. This is the partial time derivative of E. And but interestingly, they're all bilinear, right? So the momentum densities, field densities are always bilinear. And the interesting part is that, so this pi, now the field density, is locally integrable about each point charge location in the Maxwell-Bob-Landé-Thomas-Podolsky field theory. That's what Shadi and I proved. It is expected to be true for the Maxwell-Born-Infeld fields, but not proven yet. You can prove for static fields that the energy density is integrable, but nobody has any hand on dynamical Maxwell-Born-Infeld fields with moving point charges. That's a wide problem, unfortunately. But it surely falls for the Maxwell-Lorentz fields. So now let's look, for simplicity, just at the BLTP electrodynamics with a single point charge. So, right, so here is now the F, according to Mr. Newton, is the time derivative of the particle momentum, and according to Mr. Poincaré, that F is the negative time derivative of the integral of the field momentum density. Now, if you take the Bob-Landé-Thomas-Podolsky law, right, so here it is again, this monster, the sum of these bilinear terms here. So one thing you notice that D enters only in a linear fashion. H also enters only in a linear fashion. Everything else is B or E or the partial derivatives of B and E. So, and it turns out that all these fields and H depend on, when you solve the field equation, you solve them in terms of quadratures where you integrate over the particle motion. So then these fields, B, D, E, E dot, and H, can be expressed in terms of fields of integrals that contain the trajectories of the particles and also in momentum space. But D and H also depend on the acceleration, but only D and H, not B and E dot. D and H depend on A. And once again, D and H enter linearly here, so that integral over pi contains the acceleration in a linear fashion. And that doesn't change because of the d over dt here. And so that means this equation here, the star equation, is equivalent to a linear Volterra integral equation of the second kind for the acceleration as a functional of the motions q and the trajectory in momentum space. So now if you then integrate this equation over time, so you just kill the d over dt, and you do the same thing for the momentum velocity relation, dq over dt is p over square root 1 plus p squared, right? So then you get these integral equations. Q is the initialator plus an integral over time of, well, the velocity. And then what is p at time t is the initial p minus the integral from here. And so there's, of course, initial data that have to enter. And so I call that capital Q sub t and capital P sub t. They are functionals of Q and P only. Why? Well, here's, of course, the acceleration A, but the acceleration A is itself a function of P and Q. So you get actually a closed map from the cotangent bundle into itself, right? So you have trajectories in a cotangent bundle, and you can show well-posedness if this map, capital Q, capital P, is a Lipschitz map. And that's what Shadi and I proved. Namely, here's our proposition. If you give Lipschitz continuous maps from time into position and from time into momentum, and they do not need to be related now. Yeah, you just look at the integral expression. There's a Q of T tilde and a P of T tilde in there, and you just say, okay, these are C01 maps. And 01 means they are Lipschitz continuous. Here there's a Lipschitz constant V, another Lipschitz constant little a. Also, you want to have the speed of light as a speed limit. So then the Volterra equation, just by the standard theory of the linear Volterra equation of second time, has a unique continuous solution that maps T into A of T, volt phase A of T, and A of T is some functional alpha of the Q and P of T. And it depends, this alpha depends Lipschitz continuously on those trajectories. And that's all you need. That's all you need. And then you get that well-posedness of these equations, so you have unique solutions. Okay, good. So now, of course, there are a number of assumptions that enters. We have this Lipschitz assumptions here, we have the speed limit here, and so that's the reason why we do not get global well-posedness for this. No? So because maybe in the course of the evolution at some point you run into problems where whatever you chose as your maps, you can make sure that at an initial time this is fulfilled, but eventually it may be broken down. So that's one of the reasons we cannot really make a global well-posedness result. No? So let's, well, at least a little bit. So I don't spend too much time going on to the fine details, but I want to make clear where the A enters. So what is this W here? This is an upside down M, right? So it's from mass times acceleration equals force, if you want. No? So the P dot is the force. So P, of course, is not just mass times velocity here. So you get a more complicated matrix that can be inverted, and that's basically the inverse matrix here. It's now acting, you get A is this inverse mass matrix, if you want, acting on the force, and the force splits into an applied force, and that's thanks to the linearity of the field equation. You can split that, and the self force term. So that depends on the source, and it is this term that contains A. So the vacuum contribution is in fact the Lorentz force. You can show this by the same kind of integration by parts tricks that Poincare did. And here's, of course, just a regular relationship between the V and the P again. And now the source term is source force, now the self force is the same expression that Poincare brought down when P pi here contains only the contributions from the so-called self fields that the particle creates. So how do you handle that? So it's, first of all, I drop this superscript source. Then, see, here's an integral over R3, but you can show that this is the same as this integral. And because there's a d over dt in front of it, namely outside of the forward light cone of the particle, so the contribution of the particle motion doesn't matter. And so this here is actually the initial data, right? Just linearly propagating in t. So, and here you cut off everything outside. And so this is the same expression, but now you don't need to integrate over all of R cubed. You only integrate here. So then you introduce foliation by retarded spheres of these balls and work out what that is. And so you get something that involves terms called Z and Psi. Psi is just the abbreviation for the triple QVA. Psi 0 is just the straight motion, no A here, A is 0. Okay, that comes from the pi 0 here. This comes from this pi here. And so what are these Z's? Well, complicated expressions. Z's are these spherical integrals. These are retarded spheres. So you see the retardation is here. And n is a normal vector pointing from the center to the point on a sphere. And so what are these pi's? So this gets more and more complicated. There's a pi 0. Don't worry, these kernels here, I tell you later, these are Bessel function kernels. But what is important, you don't see anything in red here. Next, there's a pi 1. Now the A shows up, right? A here, A here, A here, A here, 4 times. And so you see clearly it shows up in a linear fashion. So that's the explicit terms. And pi 2 doesn't have an A again. And here are then our Bessel function kernels, J1 and J2. Okay, and having all this explicitly at your disposal, you can control this, and you can establish the Lipschitz estimates. And moreover, we can generalize this to n-point charges, and I said using the hyperbolicity. So it's thanks to the fact that away from the point charges, the electromagnetic momentum density satisfies a continuity equation, right? So you integrate all of the field momentum density pi over all of space except for some small little ball regions around each particle. Okay, so now you use the divergence theorem, right, and pull the d over dt out of this integral, and then you shrink the balls to zero on where the particles are. So these little balls, of course, means you, by the divergence theorem, so the integral of divergence of pi, divergence of the stress tensor that enters the dt of pi, is now a surface integral, right? And so you shrink this down onto the point charges. That's no problem. You don't need to take balls, so you can take anything else. So by the continuity equation. And then the change of the momentum at a particular point, right, has to be compensated by the change of momentum of the point, right? Because it cannot communicate to some other particle. No? So if I only postulate momentum conservation, I could permute around and say, the change of field momentum at this point is compensated by the change of particle momentum at another point. And mathematically you could do that, but this clearly violates relativity theory, and it seems to be a pretty eccentric choice anyhow. So the way to get the speed limit implemented is to say that any change which can only happen at the location of the particles, any change of the field momentum has to be compensated by a corresponding change of the particle momentum at that very location where the field momentum change happens. And so that's how you break it up into n laws of motion. And for those, we have the following theorem. So we have that the n-point joint Cauchy problems and the fields, Maxwell-Bondé Thomas-Polke fields, is well posed locally in time for admissible initial data. That's important. And the mass has to be non-zero, the rest masses, but they may be negative. It's globally well posed if, in a finite amount of time, no particle reaches the speed of light, no particle reaches an infinite acceleration, and no two particles reach the same location. That we cannot prove whether that never happens, right? So, but the energy momentum conservation law is rigorously justified, and one can also analyze rigorously the cell force. But there are oddities. One should not swipe them under the rug. Namely, so this field theory features longitudinal electrical waves, subluminal transversal electromagnetic wave modes, in addition to the usual Maxwell wave modes. The energy functional of the field is unbounded below, and so you need a lot of initial data, many more than the physicists normally give you. I mean, the experimentalists. So this is why one should take this really with a grain of salt, and rather as a proof of concept what we did. I'm not so sure that this is a physically deep theory here. At the same time, Feynman implemented exactly the Bob method as an ultraviolet cutoff into quantum electrodynamics. But of course, people there look usually at the scattering problem from the infinite past into the infinite future, not into the Cauchy problem. And so anyway, so I just want to point out this should be taken with a grain of salt. And so here's some literature. So this is a huge paper we have been writing for many years. There's always this window of opportunities that come and go. But hopefully in 2026, it will see the light of the day. A summary appeared already in 2019 with a correction 2020. And the scattering problem for a single particle in a given potential has been looked at by Wu Huang, Maria Radosh, and their students, and published in 2021. That was inspired by our first papers here. And they proved that this is actually well posed then globally, but of course it's a scattering problem from the infinite past to the infinite future. So none of the oddities that I mentioned happens here. And so, yeah, okay, so this was that part. And so how much time do I have, Paula?
Yeah, we have a few minutes, I would say, because we also want to allow for some questions. So
yes. So then,
what are your plans? How much?
Yeah, maybe I just show a few pictures because I want to point out that, of course, we have this complicated set of equations. What can you do with it? It's locally well posed. And I started looking at the following problem, a point charge moving along a constant electric field. And so the existing models in the literature, Abraham, Lorentz, Dirac, Landau, Lifshitz, they fail to give a radiation reaction, even though the Lamor formula says that radiation is coming out. So there's a problem that has long been recognized. So we looked at the BLTP problem, and it does have radiation reaction. So it doesn't vanish. So the question is, what is it? Now, these are very complicated expressions I showed you. So the only way so far to get a hand on it is by making an expansion in powers of kappa. That means it will converge, hopefully, for small kappa. And one really wants to get to large kappa. So I don't know how to do that yet. But at least, again, as a proof of concept that radiation reaction doesn't vanish, this is okay. So, but it shows up at third order. So to second order, it actually vanishes. No? So here's what you get. At second order, the cell force still vanishes, also in the BLTP electrodynamics. Amazingly, to order kappa 3, it becomes a relatively simple harmonic oscillator expression. That was shocking. That was done with Holly Carley. And order kappa power 4 becomes a time integral of this with a different sign. So that was done with Ryan McGuigan. And so the fifth order term looks different. So we haven't published anything there, but this is for the fourth order term. So here you see the velocity as a function of time. The blue curve, this is for positive bare mass, this is for negative bare mass. For the blue curve is a test particle motion. Then the first non-vanishing radiation reaction term is this dotted curve, and it completely overcompensates. But then when you take the correction of order kappa to the power 4 into account, then that corrects the red curve and now overpowers it. So we expect when you keep going so that this will go back and forth and so on. But as I said, this is for small kappa. It converges good here. When you blow that up, you can see that there's some convergence here. For the negative part, well, the blue curve is now a test particle motion with negative mass, goes off in the wrong direction. Then comes the order kappa 3 term, makes it even worse. But then the order kappa 4 term overcorrects and whoop, makes it look like positive bare mass, but at later times goes down and then goes up again. And what I plotted here is what Herbert Spohn calls a charge soliton. This is again test particle motion, but the mass is renormalized. It's not the bare mass, it's the bare mass plus the field energy divided by c squared that gets carried along in an adiabatic regime. And so this approximates this very well after a short time, but then departs again. So anyway, so this is just showing that one can do something with these equations, even though they look brutally complicated. And but there's a long way to go. Good. And maybe then I simply skip these kinetic theory parts that I did with Eve Elskens. So you see it gets more and more complicated. And at the end, I have a little bit on general relativity, but maybe I just say that's it. And I thank the audience and the organizers for this opportunity.
Thank you, Michael. Yeah, that was very nice and also very impressive. Or it looks like it becomes even more complicated and complicated the more you study it.
Yeah. But it is now something that is mathematically really well defined, and you can start extracting effective formulas in a systematic way with controlled error. So you don't invent ad hoc nice formulas that you suck out of thin air. So that's the advantage.
Yeah, that's impressive. I mean, I can imagine that there's a lot of work in that proof.
Yes. In fact, after a while, when you start enthusiastically working and you see how this is exploding, then you look at that and says, do I really want to do this?
Yeah, I wonder if I would want to do this.
And then you just did it. And the point is that the proof is actually shorter when you are not as ambitious as we are and just say, oh, there's a C that when the time is less than the C, then you are good. No? But what is C? So we are trying to get really numerical good estimates so that we get a practically relevant estimate for the time span on which this exists. And that's the reason why it takes so long to work this all out. There are so many estimates. And yeah.
Yeah, okay. So very nice. So let's have a question session. So if you have any question, you can raise your hand in the...
I stop sharing so that I also see who is there.
yeah, okay. Maybe that's easier then.
Very good.
Yeah. So let me also change here to see who is there.
Yeah, I see a number of friends and I see a number of names of people that I don't know.
No, that's true. So there's one question by Dirk. Please, Dirk, go ahead.
Yeah, well, I don't want to take all the question space, but if no one else asks a question, I like to use the opportunity, Michael. So I have one question, and maybe later on, but that's not so important, a comment about this Aktio-Reaktion in Wheel of Hyman. But one question about the dynamics. I mean, so I understand so far, I should think of it as a little bit like it's a local existence, but under the assumption that somehow no particles collide and so on. I mean, taking that as a, let's say the initial condition is like that, then we even have a global.
That's right. It's a little bit similar to the conditional global existence result. One could formulate that Walter Strauss and Glassie, his student, formulated for the so-called relativistic Vlasov-Maxwell model, right? That's the part that I skipped. No? That's my work with Eve Elskens, where we try to derive those equations. And so they have global well-posedness for small data. And under the condition that in finite time, the particles' velocities that stay bounded away from the speed of light, they have global existence. No? But they cannot prove whether that's true, right? And so there's an equivalent result by Kleinerman and Stafilani, and that refers to the local field energy density remaining integrable. But that's also a condition that they have to assume. And if that is true, then you have global existence. No? But it's not known whether that remains true.
Yeah.
And so here for us, we could do the same thing and then say, oh, we have global if this and this and this, which is, of course, what we do say, but we just cannot at the moment show that it doesn't happen. And I should say that Wu Hoang pointed out to us, we didn't see this ourselves, that the field energy function is unbounded below. And that is the problem. So if that would be bounded below, then you can rule out that you ever reach the speed of light, for instance, right? But in principle, a particle with, say, positive bare mass, at least, could borrow arbitrary amount of field energy that would go to minus infinity, and the particle kinetic energy goes to plus infinity, and it may do that in a finite amount of time. So at least in principle, it is conceivable because we don't have a lower bound on the energy function and on the field energy function.
I would say, I mean, Vera Hartenstein in her PhD thesis has a similar condition where she basically proved Maxwell Lorentz for point particles, but without self-advection. And there we have also just the local existence, but a global existence under the condition that the particles do not collide. But my question in that direction is, if you think about the Lorentz-Abraham-Dioc equation and these runaway solutions and so on and so forth, do we have any estimates then on stability, or can you say something about stability of these solutions? I mean, can you rule out, for example,
only in the work of Wu Huang and Maria Radosch and their students for the scattering problem. No? So they do have global existence. It's not that you start coming from the infinite past with an incoming asymptotically free motion, and then there is this obstacle, and then the particle starts doing crazy things and goes off to the speed of light. So they have a stability estimate that doesn't happen, but we don't have anything of that.
But that was in the Taylor expansion of kappa, or was it in the full model? Or do I mix it up now? Because I thought you showed.
It's only for the motion along a constant electric field.
I see.
So you don't use any Taylor expansion in powers of kappa for the well-posedness proof. No? And also Wu and Maria and their students, they don't have any Taylor expansion there. No?
So runaways you can rule out for this scenario.
For this scenario, there is no runaway. That's true. Yeah, for the scattering. So they have some bounded scattering potential, though. So I don't know what happens if you allow something unbounded. No, so.
I see. Okay. Yeah,
Okay,
thank you.
So let's allow for the next question by Fabian.
Yes, thanks. Hi. So as a follow-up on Dirk's question, you said that they use asymptotically free motion in the scattering regimes. And do they have also logarithmic corrections for the scattering trajectories in the T plus band?
You mean the work of Wu and Maria and the students? I don't remember, but so you recorded the talk. Look at the paper that I listed. It's in 2021 Journal of Mathematical Physics. No? And so it's clearly a motion where you do have quote unquote cell forces acting. No? And by the way, an interesting thing is that they really obtain from our definition of the total force through lots of integrations and controlled integration by parts. The formula that looks like a Lorentz cell force formula that was written down by Landé and Thomas in 1940 something. But Landé and Thomas, it's another case of serendipity. So they simply notice that in a certain integral representation of the electric and magnetic fields E and B, right? So they do a transformation of integration variables under the integral. Huh? And so then if you evaluate that expression for E and B on the world line of a particle, so it's a representation where you integrate over all of the past motion of the particle. You know? You come from minus infinity in time. And then you evaluate it at the location. That gives a vector that is actually mathematically defined. But it is not the limit of the electric and magnetic fields as you approach that point when you come from the neighborhood. No? So there's no limit. No? So it's something that jumps and has a vector value. But if you change variables, then that doesn't even converge. No? So they just accidentally chose these variables. And it turns out that Wu Huang and Maria showed that from our definition, that's the formula we get.
Okay, I see. Nice.
But we cannot use it in an initial value problem because you integrate over the true motion of the particle over the infinite past. Right? So this formula doesn't work for an initial value problem, but it works for the scattering problem where you come from the infinite past and go into the infinite future.
I see. I also have a question regarding the initial value problem formulation that you put on the slide at some point. And you said that it has very many initial values for the V, the H, the E field derivatives.
All of the Klein-Gordon operator. That's right. That is in the law. And so you need not only two field values, field vectors that you normally have, you need actually four, right, in total, four three-dimensional field vectors. And so none of these authors bothered about that, but neither did Feynman when he put that into quantum electrodynamics, and neither did Pauli and Vilas, who made it even worse. Now, when you look at the Pauli-Vilas regularization, they take powers of the Klein-Gordon operator acting. Yeah, so each time you get more derivatives when you want to have an initial value problem. But of course, nobody in quantum electrodynamics looks at an initial value problem. They all look at the S matrix. No?
But is there a compelling heuristical reasoning on which behalf you can reduce the number of initial values, so that you say you have conductors around or you leave something to be for a long while?
Shadi and I point out in our write-up that, again, has not yet been published, but that you can, of course, try to map these extra initial data I'm sorry, map the anyhow given initial data into extra initial data, no? So that you tie them up. No? And so we tried something, namely to maximize the field energy integral given the initial data that you would normally pose anyhow. Right? And so you maximize with respect to the remaining degrees of freedom that the BLTP law has. And that gives a formula that looks actually interesting. Now, whether that's the right thing to do, we don't know. No? But we have thought about exactly what you just asked.
And if Paula doesn't mind, I have one other
ask another question.
Okay. Is it your intention to analyze these dynamics for different kappa parameters and in the end put kappa to infinity to really remove this constant?
We want to get kappa very large, but I don't think kappa to infinity will work, no? Because formally kappa to infinity gives you back Maxwell-Lorentz. No? And the problem is because we have a paper, Holly Carley, who I mentioned and showed in the talk, joined with Volker Perlich, where we try to estimate the effects of this Bob van de Thomas Podolsky modification of electrodynamics onto the hydrogen spectrum. Okay, and so given this, the accuracy with which the hydrogen spectrum is known, it turns out that kappa has to be enormously large, right? Meaning, however, also that the field energy of a point charge is huge. So now in the scattering, one doesn't expect that the energy conservation and momentum conservation that you see is actually always a total. It's not just the bare mass and bare momentum or so, but it's the dressed particle. And if the field energy is huge, then the particle has to have a very negative bare mass. Yeah, so that's what we found. And but we cannot let kappa go to infinity. You know? So it's but when kappa is huge, you cannot do any expansion. Huh? So you can also not expand in powers of 1 over kappa because 1 over kappa to 0 means kappa is infinity and you have Maxwell-Lorentz, and then you cannot expand around this. No? So I really don't know what to do at the moment there.
I mean, at least if you don't want to turn to the limit, you should at least show some continuity. If you pick kappa this large, then picking it a bit larger won't alter your dynamics too much anymore. Right? Otherwise, you're open to the same criticism that you put towards the upper model, that if you take different shapes, then you get whatever force you like.
Yeah, no, it's a point that people always have with quantum electrodynamics with the ultraviolet cutoffs. You want to remove them, but you get stuck at whatever 27 GeV or so, I forgot. And so
at least in these formal expressions, you have some form of continuity with respect to this parameter.
That would be nice. Yeah, then one could say, okay, so maybe the originally formulated Lorentz electrodynamics doesn't exist, no, but some kind of asymptotic regime exists that one can extract, possibly. Yeah, but this is a long way to go. No?
All right, thanks a lot.
Sure.
Okay, thanks. So there's another question or comment by Dirk.
I guess a comment comes now.
Comment, that was clear.
The comment is not so important. Yeah, but maybe before I ask my question, I like to encourage also the audience that we don't, that somehow moderators or organizers don't take away all the questions. So if there's a good question from the audience, please go ahead before my question.
If not, you may ask.
If not, I'll go.
Very high. You said if there's a good question, you should have said
okay. If there's any question, no. We have a good audience, so all the questions are good. No.
Into the chat, there were only thanks. There was no question in the chat.
Yeah, no, also in the chat, none. Yeah, so let me ask another question, maybe two questions. So one question would be, of course, I mean, it seems you also have to do a mass normalization to make contact with the experiment. Could you describe this a little bit, maybe compare it also to what people do in this rigid charges, Maxwell-Lorentz?
Yeah. The point is that when you as I said, come from the idea that kappa has to be very large in order to match experimental data in a spectroscopy, let's say. And then, wow, then coming from the scattering experiments, that means bare mass has to be negative. Now you look at the initial value problem, and you see, of course, initially the particle, it's the bare mass that couples, the bare inertia couples to the shows, I should say, not couples. The bare inertia shows in the motion first, and only later the dressing shows up. No? So that means the shot, so to speak, goes off in the wrong direction and has to be corrected. So the interesting thing is that we see, at least at order kappa 4, it suddenly shows up being corrected. No? Of course, when you push that for too large times, then the small kappa expansion is out of the window, and indeed it starts doing crazy things. So this is all very preliminary, but if that doesn't show up, for instance, to come out for a non-perturbative treatment, that you get this correction of the motion that initially goes off in the wrong direction with negative bare mass, then you can trash the model. No?
Because I mean, if you take, for example, let's say a charge model where you have rigid balls of some radius, I mean, you maybe recall this result by Gernot Bauer and Detlef Dürr, where they basically showed that usually these particles that go along straight lines, if you perturb them only a little epsilon, and you give a negative mass, then you immediately get similar behavior than the runaways, and that would be my question. So usually, this behavior in the classical, or let's say in the classical, I mean in the orthodox Maxwell-Lorentz theory, shows up at around radius, the classical charge radius of an electron.
Yep.
That's why I also ask a little bit about stability. I mean, if you do this mass optimization in your theory, do you have the hope then that the self-reaction force is so correct that it will not show up? I mean, in leading order, it should have the exponential instability somehow. But do you think like the force that you have overrides this behavior and keeps the model
I
stable?
don't know. And I wouldn't say I have that hope, no, because I don't feel really strongly invested in that BLTP theory. No? So that's why I pointed out these oddities. I really worked on this I can say, in desperation. I really want to do Born-Infeld, but it's so difficult. And at the same time, I wanted to see whether my ideas work, right? And so then at some point you swallow that toad and say, let's do this BLTP. At least the field theory is linear, and the first 50% of the problem you can get a hand on, and then start working hard on the dynamics. And so, yeah, now that it's there, we want to find out what it does. No? And but if it behaves in a crazy way, then I don't feel that, so sad. No? So I feel sorry for the BLTP theory there. But as I said, this is just, I try to get my hands on it and learn something about it. But in principle, of course, with Born-Infeld, for instance, suppose one gets the hands on it, I would expect similar problems, that the Born parameter has to be chosen also such that you will be forced to put a negative bare mass, and then you have the same questions popping up again.
I see.
Negative bare mass. And so it's, but yeah, one has to see. No? So it's difficult to predict the future here. And but I hope that many more people will join. Oh, look, I'm getting older now, so we need young blood here that takes over and keeps pushing. No?
Yeah, a very impressive work. Yeah, thanks. Thanks
Yeah.
for the answer.
Thank you. Thank you.
Yeah, maybe Fabian will join.
My PhD students are not for sale.
Later
No,
on.
but there's a time after the PhD, Fabian, where you can do whatever you want.
Okay, last remark by Fabian.
Yes, you mentioned before that this BLTP model was a role model for the cutoff QED. With this, you mean Pauli-Villars regularization, or which one?
No,
Did
that's
you mentioned?
it's paper by Feynman in, I think, 49 maybe, or early 50s. And he calls it an relativistic ultraviolet cutoff for electrodynamics. And so then somewhere in the middle of the paper, he mentions Bob's work. So he's aware of Bob. He doesn't mention Londet Thomas. He doesn't mention Podolsky. And but then, of course, in that paper, this is just also the Bob Klein-Gordon operator there. This renormalization business comes later, no? So I don't recall that this is in the paper. No? So ultimately, people want to remove this cutoff or let kappa go to infinity. No? No? So, but in this original paper, but since it non-perturbatively, it looks very much so that you cannot remove it. So there is a hint that there is some extra parameter, and I don't believe that it is a good explanation to say, that shows that we cannot formulate an electrodynamics without the other forces of nature. No? So we may just think wrongly about electrodynamics, as already Gustav Mie pointed out. No? So and Poincaré, if you want, that by assuming that you have charges that move, whether they are points or smeared out, right? So, but you have a conservation law, you get the so-called pre-metric Maxwell equations for free. That means for the fields D, E, B, and H. And now you need a vacuum law. So who tells you that B equals H and E equals D is the right thing? No? So that's clear that there is a lot of room for improvement, and maybe there is some small parameter that nature has supplied, and who knows, no?
All right, thanks.
Sure.
Okay, thank you, Michael. So I think if there are no further questions, let's thank you again, and
thanks for having me.
Thanks for coming.
Okay, and enjoy the rest of the day. And
same.
It was really great having you.
Thank you, and hope to see you all soon.
Yeah, it was really impressive, that work that Shadi and you have been doing. So yeah.
Thank you. Thank you.
Hope to see each other and also in the next couple of events. So on the 26th of January, we have Vincent Lam, a philosopher, so on laws of nature and space-time. On the 2nd of February, we have Volker Bach, who will report on descriptions of many particle systems and in general effective theories. So the program goes a little bit on, but then comes to the semester break also on our side. Yeah, Michael, I wish you all the best for the start of the semester. Same to you, Shadi. I think
thank you.
It starts at the same time, and hope to see you guys all soon.
Okay.
Hope to see you soon. Bye.
Bye. Thanks a lot.
Bye.